In this video, we're going to look at term-by-term differentiation and integration specifically for a power series. We'll begin by defining our f of x to be the power series, the summation of c sub n times the quantity x minus a, in which the quantity is raised to the nth power, as n goes from 0 to infinity. But we're going to define the power series to have a radius of convergence r, which is greater than 0, meaning it's going to be more than just the one single point at the center. When we have that set up, we will be able to say f of x is differentiable and thus continuous on the interval from a minus r to a plus r, so center out to its radius on both sides. Notice we are not including the endpoints. We'll have to deal with that later. Now, if the radius was by chance of convergence infinity, we don't have to worry about that because it would be all reals. When we have this information, we can actually go ahead and find that f prime of x is equal to the summation of n times c sub n times the quantity x minus a raised to the n minus 1. That's right, applying the power rule to what we have up here, taking that n, moving it to the front, multiplying it to c sub n, and then taking our quantity, reducing it by 1 degree. Now you'll notice our summation does start at 1 and goes to infinity compared to before going to 0. Because why do we need c sub 0 when, to worry about that, when c sub 0's derivative, being a constant, will go to 0. So we'll just start immediately with c sub 1, and then we'll add 2 times c sub 2 times x minus a, which is the derivative of this piece, and then we'll go 3 times c sub 3 of x minus a quantity squared, which is the derivative of that piece, and so on. We can also continue on and realize that if we can differentiate, we can also integrate. So we can basically do the power rule in reverse. We can raise everything to the plus 1 power than it was before. So here, c sub 0 now gets multiplied by x minus a to the first power, but then has to be divided by 1, hence why it's n plus 1 on the bottom. And if we're going to take this and integrate that term, we'll raise it to the second power, but then we'll have to take c sub 1 divided by 2. If we take the integral of this term, and we'll have to raise the 2 to the third power, but then divide by 3. So that's why you see c sub 1, the 1 there, is going to be divided by 2, which is 1 plus 1, and the 2 here is represented here, and that's 2 plus 1, which is 3, and so on. Just remember, both of these series will have the same radius of convergence r. All I'm saying is it has the same radius. It does not imply that the interval of convergence is the same. Let's begin by looking at the example of the fraction 1 over 1 plus x squared. And let's treat it as a converging geometric series in which it really is the sum of 1 over 1 minus the quantity of negative x squared. If we do that, then we could write it as a summation of negative x squared, all raised to the nth power, as n goes from 0 to infinity. But that means that this would actually be an alternating series, so I could pull out the negative 1 raised to the n and keep x raised to the 2n as a separate piece of the summation. So I could then write the actual sum as 1 minus x squared plus x to the fourth minus x to the sixth plus so on. So why couldn't we go ahead and integrate 1 over 1 plus x squared dx? If we did, the negative 1 would still be raised to the n because remember, it's a dx problem and negative 1 has nothing to do with the x, so that just stays the way it is. The x to the 2n, on the other hand, well, that part is actually going to get integrated, and you're going to see that now it's going to be x to the 2n plus 1, but of course we'll have to divide by the 2n plus 1. Don't forget to include the plus constant that, we don't really know what it is, hence why we call it plus c. If we then work out that term, you'll now note that we can write this as c plus x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, which is exactly what it would be if I had anti-differentiated each of the individual terms above. So, what do we know about the integral of 1 over 1 plus x squared dx? We also know that that's tangent inverse of x. We've learned that tangent inverse derivative is 1 over 1 plus x squared, so now we're going in reverse. So what we just established is that tangent inverse of x is going to end up equaling the equation above. But we got to remember that tangent inverse of 0 has to be 0, therefore c equals 0, and so now I can now set tangent inverse of x to be the summation of negative 1, all raised to the nth power, times x raised to the 2n plus 1, all over 2n plus 1 as n goes from 0 to infinity. Now, since both series had a radius of equal to 1, we can establish that tangent inverse of x is going to have an interval including from -1 to 1, including the endpoints. So if I wanted to go ahead and approximate tangent inverse of 0.5 to the 7th order, I can go ahead and plug the 0.5 into our formula right here, remember this being 0. And that's what I'm about to do. So if I plug the 0.5 into the x spot there, I've produced the 0.5, like I said, was going to be put here and here and here and here. That being 0 is gone. And so I came up with a value of 0.4634672619. Now remember, that's an approximation. Why am I making a big deal about this being approximation? Because we would like to also know how close we are to the actual answer. And since tangent inverse of x is a power series, and this power series originally up here was alternating, it's still alternating down here. And because it's alternating, we can apply that alternating series estimation theorem we learned some lessons ago. And what was that again? That's in which the error of our approximation, in this case tangent inverse of 0.5 minus the value that we got down here. I can actually figure out what tangent inverse of is, and when I say figure it out, the calculator will figure it out for me, and I can figure out that right now I was off by 0.0001835. Now that's what I knew I was off of. Maybe I don't know what the tangent inverse of 0.5 actually is, but with the alternating series estimation theorem, what I just needed to do is I had to go to the next first omitted term, and that will be less than that. So what would have been my next term? Well, I would just have to continue on the sequence. So if this is going negative x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7, then the next piece would have been plus x to the ninth over 9. And I would have plugged my 0.5 into that spot, which I did here, here, and here, because, well, it's the same thing all the way down. And what the estimation theorem is, specifically the alternating series estimation theorem is that I may not know exactly what tangent inverse is, but I would have known that this estimate would have been within 0.0002170013. And as I've shown you, we already know it was below that. So the idea is I'll still have a good idea how close I was to my answer, even if I don't know it, because I can just look at the next term and just say, this is the largest it's going to be off by, and so be it. There it is. I have one more fraction I want to look at, which in this case is 1 all over 1 plus x. And if again we treated it as a converging geometric series sum, which could have been written as 1 all over 1 minus negative x, then I could rewrite it also as a summation of negative x quantity raised to the nth power as n goes from 0 to infinity. This is still an alternating series, so I could rewrite it as negative 1 raised to the n, x to the n of the same summation. Which then, of course, means I could rewrite that as 1 minus x plus x squared minus x cubed plus, well, continue it on. In this case, I just want to go directly to the integration of 1 over 1 plus x dx. That means I would like to integrate the summation of that same negative 1 to the n, x to the n, dx as n goes from 0 to infinity. Again, why would I want to do that? Because I can apply the power rule. Well, the power rule in reverse, meaning I would have to take x and raise that to the n plus 1, but then divide by my new exponent n plus 1. Remember, negative 1 is not affected by x, therefore we do not change that exponent there. And because it's integration and we don't know how our first term started, don't forget to include the plus c. So if we wrote out our new expanded series this way, we would go c plus x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Again, it's the same if we had anti-differentiated each individual terms above and then include our plus c. Now, what exactly is the integral of 1 over 1 plus x dx? Well, if we did our u substitution and said 1 plus x is equal to u, then our du would be equal to dx, and we would have an integral of 1 over u, which is the natural log of u. So I guess we're saying is the integral of 1 over 1 plus x dx actually is the natural log of the quantity 1 plus x. But I'm going to need to establish my c, so I'll plug in something that I know. For instance, make x equal to 0, and we'll have ln of 1. We'll make that equal to 0 because, well, it is equal to 0. What I'm getting at is we've established that c is equal to 0. And so now we can rewrite ln of quantity 1 plus x straight up as the summation of negative 1 to the n times x to the n plus 1 all over n plus 1 as n goes from 0 to infinity. What we're going to do now is we're going to do a little bit of algebraic manipulation because what I want to do is make my summation just a little easier. Wouldn't it be nice if we could just have n and not n plus 1? So what I've decided to do is I'm going to subtract 1 from my values of n. So this is kind of what I did. I went n plus 1 and I went minus 1. I did that for my exponent, I did it for my denominator. But I have to also make sure my terms line up in the alternating series, so that my positive term is going to be the positive term that it was before. And so I had to adjust, in this case, the negative 1 to also be raised to the n minus 1. But I counteracted that by having it set to n equal to 1. So notice it's no longer n equal to 0, it's now n equal to 1. And because of that, I can actually now write it a little simpler. I can say instead that ln of the quantity 1 plus x is actually the summation of negative 1 to the n minus 1. Okay, so that may be just a teeny bit tougher, but it's so much easier to then do x to the n all over n. And now just have it go from n equals 1 to infinity. Both of these series had a radius of convergence of 1. We will realize that ln of the quantity 1 plus x is going to have an interval convergence going from negative 1 to 1. It will include 1. It cannot include negative 1, and that's just because you can't take the ln of 0. So, that explains that right there. So if I'm going to go ahead and approximate the ln of 0.9 to the third order, just remember that if I'm doing ln of 0.9, I'm not making x 0.9. I'm starting with ln of 1 plus x. So I'm going to have to think of it as ln of 1 plus negative 0.1. So that's going to be the value of x, negative 0.1, that I'm going to proceed to put in here, and here, and here, and here, well, specifically here. And that's what I did for the third order. I just had to go negative 0.1 minus the quantity negative 0.1 squared over 2 plus the quantity negative 0.1 quantity raised to the third power all over 3. And I approximated it to be negative 0.105333 repeating. Now, although the series for ln of 1 plus x initially looks like it will alternate, what will happen is that if we plug in the value of x equal to negative 0.1 for ln of 0.9, this actually leads to a non-alternating series. Okay, let's take a look here. This is negative. A negative squared is positive, but this is negative. So this is negative, and then a negative cubed is going to be negative again. We're back to being non-alternating. And so there it is, kind of worked out with the many extra terms. And so I cannot go ahead and apply the alternating series estimation theorem. So even though I want to do all this kind of work, what I'm going to have to find out is a different way to come up with this value of estimating and realizing how far off my error actually is. Okay? And for that, we will need to apply Lagrange's error bound.